Well, it's Jack again. We're going to talk now about Chapter 2 in the Introduction to Theoretical Chemistry, 2nd edition. I remind you, here's the website where you can download it. So in Chapter 2, this deals with what I call a lot of model problems that are more or less the first applications of quantum mechanics that you're going to learn in this book. The first model problem is free electron motion in polyenes, and this basically is a one-electron particle-in-a-box model in a one-dimensional particle-in-a-box where electrons move along the conjugated pi orbitals of polyenes. And basically it's particle-in-a-box being applied to a polyene molecule, but it is one of the most important models that most practicing theoretical chemists think of when they think about electrons moving in conjugated systems. And then after doing that, we move on to treat the same kind of problem, but in 2 and 3 dimensions. We call these bands of orbitals in solids. If the orbital is involved in motion on a surface of a solid, so it's only in 2 dimensions, then we call that a solid surface band, or band is basically just a grouping of orbitals. And then if instead it's in 3 dimensions, then it's like electrons moving throughout the 3-dimensional x, y, and z coordinates within a metallic solid. And they're only metallic solids because that's where electrons will tend to move freely. A solid like diamond or silicon would not be metallic because the electrons there are more tightly held to the valence regions of the atoms. So this free electron motion is applicable to metallic type states in 2 and 3 dimensions. Then we move on to talk about what we call the Huckel or tight binding theory. And this is just the simplest model that chemists use to describe covalent bonds between pairs of atoms or triplets of atoms. So you bring 2 atoms together with their valence orbitals pointing toward one another, and they form a bonding or anti-bonding orbital. If there's 3 orbitals, for example, like in cyclic, like a 3-membered ring that has 3 pi orbitals, then you might form a bonding, a non-bonding, and an anti-bonding orbital. So that's basically the Huckel or tight binding description of chemical bonding. Then we move on to talk about electrons moving in atoms. We call these hydrogenic orbitals, where electrons move radially and then they move in 2 angular coordinates. So we have a Schrödinger equation that's in 3 dimensions, phi, theta, and radial dimension. And so we have to solve a 3-dimensional Schrödinger equation. And the properties that come out of this, of course, are the well-known S, P, D, and so forth shaped orbitals that you're familiar with from introductory chemistry, and then the radial components of these orbitals. You know, the 1s and the 2s and the 3s and the 4s have different radial characteristics. And then there's a treatment of electron tunneling. This is something that usually isn't treated too much in introductory texts, but there are states in atoms and molecules where the electrons are actually not permanently bound to the molecule. They're called metastable resonance states. And these electrons tend to be held toward the molecule by some valence range attractive potential, but then they actually have energies that are above their ionization thresholds, and the electron can tunnel out and escape and undergo what is called auto-detachment or auto-ionization. So that's another problem that is in this chapter that's very important to learn about. Then we spend quite a bit of time talking about angular momentum. You know, there's orbital angular momentum in atoms. Electrons move around in p and d and so forth orbitals, but they also have spin angular momentum, and nuclei have intrinsic spin angular momentum. And all these angular momenta share characteristics that we talk about in this properties of general angular momentum. And then sometimes when you have 2 or more kinds of angular momenta, like an electron in a p orbital of an atom, you have the orbital angular momentum, and then the electron has spin angular momentum, and spin-orbit coupling causes one to have to talk about coupling these angular momenta. So you have to learn about forming singlet and triplet states and quartet states and doublet states and all kinds of angular momentum coupled states. And then there's another kind of angular momentum that deals with rotations of molecules. And a linear molecule, of course, or a diatomic molecule can rotate in 2 axes when it rotates in space. If it's constrained to lie flat on a plane, it then only spins around 1 angular axis. And then a polyatomic molecule actually can spin in 3 different axes. So treatments of rotations of linear or diatomic molecules and polyatomic molecules is a lot of the study of angular momentum. Then we have to treat also the simplest models for vibrations of molecules. And the way we think of this is each bond in the molecule undergoes a sort of independent vibrational motion that we call harmonic oscillation. And that's what's covered in the vibrations of molecules component of this chapter. And then just as with all other chapters, there's a summary that I will present at the end.